Okay, we're in chapter 4, and we have a kingdom, king, K-I-N-G, kingdom of no multiply. Okay, so in this kingdom, I can't multiply. The king has said so. So here I am, kingdom. There's no multiply, no times at all. Can't divide either. Can't divide or multiply. So what are you going to do in this kingdom if you can't divide or multiply? Well, you can add a lot. 2 plus 2 plus 2 plus 2, right? But the king said no multiplying, no division. Okay, so you're a smart mathematician, so what you're going to do is you're going to go and keep the king's word. You're not going to multiply. You're going to come over to the land of L-A-N-D, the land of log over here. Okay, so you're going to send, you got an A and you have a B, and you want to multiply them over here, but you can't do that, right? So you're going to send A and B over to the land of log, and you're going to find the log of A, and you're going to find the log of B, and you're going to add them because that's what the king wants. Okay? And then once they're added together, you're going to come back the other way, and on the way back you're going to take an anti-log, and you're going to get the right number. Ba-bam! So that's what you're going to do. And now you've done what the king said. No multiplying, no division. I can subtract logs, right? But I'm not going to divide. Just going to subtract. And the king is perfectly happy. You're not multiplying. You're not dividing. Okay? But you are getting the right answer. So isn't that cool? So we do the same thing in chapter 4. What we do in chapter 4 is we have a differential equation that's in the time domain. So y of t, y prime of t, y double prime of t. We take it and we do a transform of that into the S domain. And in the S domain, we're going to do 9th grade algebra. Well, maybe not. Algebra, anyway. We're going to do 9th grade algebra on whatever it is we have from the time domain. And then we're going to come back. So over here we're going to do a Laplace transform on the way over to the S domain. And we're going to do an inverse Laplace transform back. And now we're going to have the answer without doing any trig. So we're going to do an answer without calculus. Isn't that great? Until we get to section 4 of the book, and then we integrate and differentiate our Laplace transforms, and then we start using calculus again. But in the meantime, we don't have to use calculus to solve the differential equations. We can use Laplace transforms, which is what a normal engineer will do with his life. That's what he's going to do. All right, so what is this Laplace transform? I have a function f of x, and I take the Laplace transform of f of x, and I get f of s, capital F. So my capital letters of s are, and this is probably, we'll use a t here for time. So I'm in the time domain. I take the Laplace transform in the time domain. I get f of s, capital F of s, and that's my Laplace transform. So this Laplace transform is going to be integral 0 to infinity of the f of t times e to the minus st dt. That's how I'm going to get it. Isn't that cool? And yeah, that's what we're going to do. All right, so now what we're going to do is we're going to make a Laplace transform table. We're going to come up with f of t's, and we're going to find the Laplace transforms, and we're going to keep them so that when it's time to do a Laplace transform, we don't have to do the integral. We can just go to our Laplace transform table and get it. Okay, so that's the plan. So somebody out there, give me a function. Okay, that's excellent. F of t is equal to 1. Yeah, that's a good function. Very nice. Yeah, okay, guys. All right, so now I'm looking at the Laplace transform of this guy is going to be the integral from 0 to infinity, f of t, e to the minus st dt. All right, can I do that? No, we're not allowed to take integrals 0 to infinity, right? So we're hosed already. So we'll go with limit b goes to infinity, integral 0 to b, the normal mathematical thing, so that we can do what we can't do, right? Yeah. E to the minus st dt. All right, so that's going to be limit b goes to infinity, e to the minus st divided by minus s, evaluated at 0 and b. Okay, so I got limit b goes to infinity, e to the minus sb over minus s minus e to the 0 over minus s. Okay. As b goes to infinity, this guy goes to 0, and I end up with minus a minus 1 over s. So if I have the function, if f of t is 1, then its Laplace transform is 1 over s. I write that down, I remember it, I keep it. All right. Now we'll go back to our game. Somebody give me a function. Just any function at all. Oh, excellent choice. Just gorgeous choice. F of x is equal to x. Oh, what a great choice that was. All right, well, f of x is equal to x, so the Laplace transform is going to be integral 0 to infinity, x e to the minus st, well, it'd be, we'll change the variable. We'll make it all t. That'd be better. All right. T, dt. All right, well, I can't do that either because I can't go to infinity. All right, so limit b goes to infinity, integral 0 to b, t e to the minus st dt. And I study that for a little while, and I look in the integral table, and I decide what? Integration by parts. Oh, okay, no problem. So I got uv prime, u prime v minus plus v prime u. So if I have v prime u is going to equal uv prime minus u prime v, and I integrate everything, then I'm going to have the integral of v prime u is equal to the integral of, is equal to uv minus the integral of u prime v. Okay? So now the issue is, what is u and what is v? So u is going to be t, and u prime is going to be 1, and that makes v prime equal to e to the minus st, and v is going to be minus e to the minus st over s, right? Okay, so limit b goes to infinity. And don't tell me you don't remember this. You guys are in Calculus 3. They have to remember how to do integration by parts. T e to the minus st dt equals u v. What's u? So that'd be t minus e to the minus st over s, evaluated at 0 and b. You did remember to do that, right? Integral 0 to b u prime, which is 1, v, which is minus e to the minus st over s dt, close bracket. Now, it would have been better to do that in a different color, and I apologize for that running together ever so slightly. All right, so I've got limit b goes to infinity, and I've got the guy that I want. Is equal to, okay, I put a b in there, so I got a b. I've got a minus e to the minus sb divided by s, minus, I put the 0 in, 0. Okay, so I've got that. And then I've got minus that integral. That looks like e to the minus st over s squared, evaluated at 0 and b. And I need another bracket over here. All right, now, b goes to infinity. b is infinity, right? Minus e to the minus st, that's on the bottom, right? Who goes to infinity first? Use L'Hopital's rule, this becomes a 1, this is still getting negative, that guy's a 0. Good enough? Okay, good enough. So now I've got integral 0 to b, limit b goes to infinity, t e to the minus st dt equals, I got a minus, I put in the b, I got a limit b goes to infinity, in case anybody's wondering. I put in the b, e to the minus sb over s squared minus 1 over s squared. That guy goes to 0. This guy goes to 1 over s squared. Thank you very much. Now we know the if that's an x, 1 over s squared. Isn't that lovely? Didn't that just work out just fine? Now we have a table of Laplace Transform somewhere. And it says that if I have x to the n, and I'm gonna go and replace these guys with t's. Okay, so I got a t there and a t. So if I have t to the n, I'm going to have n factorial divided by s to the n plus 1. So if I happen to have an n squared or an n cubed, I can do those two. Now, if I had an n cubed, right, if I had a t cubed, then I'd have to do integration by parts 3 times to get the answer. That'd be a pain, right? Yeah, pretty much. But that's what I'd have to do. All right. I guess, okay, give me another function.
X squared.
X squared. We're not going to do x squared. I got to do it twice. All right. In fact, I just did x squared. I just told you what I want. All right. So we'll do, seeing that you guys are just so wonderful, we're going to do e to the at. How's that? So f of s is equal to integral 0 to infinity. It doesn't look like an infinity. E to the at, e to the minus st dt. All right, so that's what we got to do. Limit b goes to infinity, integral 0 to b, e to the a minus s t dt. All right. Limit b goes to infinity, e to the a minus s t divided by a minus s evaluated at 0 and b. Okay, looking good so far. Limit b goes to infinity, e to the a minus s b over a minus s minus 1 over a minus s. Okay, this guy goes to 0 again. Can s be bigger than a? Yeah, it might be. Who knows? And I got a minus sign there, so I'm going to have 1 over s minus a. Okay, so we'll go put that on our table. And we have that e to the at is going to be having a Laplace transform of s minus a. What if it was e to the minus at? What would it be? E to the minus at, what would I have? 1 over s plus a, in case you're wondering. Okay. Which begs the other issue, which we haven't really discussed yet, but if I have f of t plus g of t, then my Laplace transform is going to be f of s plus g of s. So additive works, and if I have a f of t, then my Laplace transform is going to be a f of s. Okay, because that a can go in and out of the integral sign and just be there. Okay, well, we need to have more fun. Somebody have another function they'd like me to do?
Hypercosine. Hyperbolic cosine.
All right, well, hyperbolic cosine is already done.
Oh, you mean one that's not on this list?
No, it's already done. Hyperbolic cosine of x, right, is e to the x minus e to the minus x over 2. So that's e to the x over 2 minus e to the minus x over 2. And so the Laplace transform of the hyperbolic cosine is going to be this guy minus that guy. We already solved those, right? So that's going to be 1 over 2 s minus x minus 1 over 2 s plus x. And now we find a common denominator and add it together and we get what's there. So we already did it. You just didn't know you did. All right, well, that was simple. Okay, so come up with something worthwhile. All right, so we're gonna do e f of t is equal to e to the j omega t, where j is the imaginary operator in the square root of minus 1. How's that? Will that be okay? Can we do that one? That'd be all right to do? Okay, so that's the one. Anybody want to do it on the board for me? I mean, these things have been pretty easy so far. Anybody want to go do that one on the board? No one's moving for the record. No one's moving for the board. Okay, so I want f of s integral 0 to infinity e to the j omega t, e to the minus st dt. All right, so that's what I got. Limit, and I got plenty of room, right? Because I'm not going to run out of room. B goes to infinity. Integral 0 to b, e to the j omega minus s t dt. All right, limit. B goes to infinity. E to the j omega minus s t divided by j omega minus s, evaluated at 0 and b. Okay, front row, we were supposed to tell me if I make a mistake, you know. For the record, there is no front row. Everybody's sitting in the second row. Okay, just wanted to make sure. All right, so I've got limit. B goes to infinity. Now, have we done any? Well, we have. I guess we did do integration. So e to the j omega minus s b over j omega minus s minus 1 over j omega minus s. Okay, is that all there is? Yeah, pretty much. All right, well, this guy goes to 0 again. And so my f of s becomes 1 over s minus j omega. I take that minus sign, put it over there. Now, your 9th grade algebra teacher would tell you what about radicals in the denominator? Not allowed, right? So we can't stop, right? So we have to get rid of the radical in the denominator, right? So we're going to have to multiply top and bottom by the complex conjugate, s plus j omega. S plus j omega. All right. So that you would have known to do that, right? You wouldn't have left the j on the bottom. Yeah, of course you wouldn't have. All right, so I've got s plus j omega divided by s squared plus omega squared, right? Yeah, s squared plus omega squared. Now I have I'm rational down there. Okay, so this becomes s over s squared plus omega squared plus j omega over s squared plus omega squared. Well, are we done? Wow, looks like we're done. Wow. Wait a minute, I got an imaginary operator here. Back to e to the j omega t. What is that? What is that function? E to the j omega t. What is e to the I t? Cosine t plus I sine t, right? Remember that? Imaginary operator there in the e guy, right? E to the I t is, remember that? Oh, you don't remember that. You might remember that. You could remember that if I told you remembered it. Okay, so that being the case, e to the j omega t has to be cosine omega t plus j sine omega t. Okay, and the Laplace transform of j omega t is the Laplace transform of the cosine plus j, the Laplace transform of the sine, meaning the Laplace transform of cosine omega t is going to be s over s squared plus omega, and the Laplace transform of the sine of omega t is going to be k omega over s squared plus omega squared. squared. Okay, that cool? So now we just solved for Laplace transform of cosine and sine. All right. So we'll do one more. No, we'll do many more, but we'll do another one. Okay, so f of t is equal to 1, or it could be equal to 0, or it could be equal to 2, or it could be equal to t. Okay, so it's equal to 1 for 0 less than or equal to t less than or equal to 1. It's equal to 0 from there to 2. It's equal to 2 from there to 3. And if I'm greater than 3 to infinity, it's t. And now I want to find the Laplace transform of f of t. Sounds like something I'd do on the test, right? Yeah, something like that. I might do something like that. Probably be weirder than that, but I might do something like that. All right, so I want the integral 0 to infinity f of t e to the minus st dt. That's what I'm looking for. All right, so we're going to have to, what do we call it? We're going to have to, is it called partition the interval? It's called, I forget what it's called. All right, so we're going to go integral 0 to 1 of 1 e to the minus st dt plus integral from 1 to 2 of 0 times e to the, I like that one, plus integral 2 to 3 of 2 e to the minus st dt plus integral 3 to infinity of t e to the minus st dt. Oh, it looks like I got another integration by parts to do. Bummer. Anyway, just another cross we have to bear. All right, so I've got e to the minus st divided by minus s evaluated at 0 and 1 plus 0 plus the integral plus plus 2 e to the minus st over minus s evaluated 2 to 3 plus integral 0 to infinity t e to the minus st dt. Okay, well, let's see. I can do the top guy here. I put a 1 in, and I get e to the minus s, e to the minus s, e to the minus s divided by minus s minus a minus, making it a plus 1 over s. This guy goes away. Plus, I've got I put a 3 in, 2e to the minus 3s over minus s minus 2e to the minus 2s over minus s plus whatever else it is that I have left over. Plus integral 0 to infinity t e to the minus st dt. Now, I've already done this integral once by integration by parts. It would seem like I should just go get it, right? Can I do that? Where was that? That wasn't here. That was there, right? I've already done it once. So it's t minus e to the minus st over s. All right, so t, fine. This will be okay. See, I can just copy it over. Copy, boom. There we go. I just go get the integral. Then I won't have to do integration by parts again. Looks like he's in the wrong spot. Move him up one. Yeah, that's good. So I'm back to here. I'm back to where I'm supposed to be. All right, so how am I going to handle that? Okay, so I've got 1 over s minus e to the minus s over s plus 2e to the minus 2s over s minus 2e to the minus 3s over s plus integral 0 to infinity t e to the minus st dt. And this isn't 0 to infinity, this is 3, right? 3 to infinity. 3 to infinity. 3 to infinity. Okay, now edit, paste. All right, so I'm going to go 3 to infinity, 3 to infinity. 3, 3, and I still have to take limit b is going to infinity. Okay, so I still have to do that. All right, so I got limit b goes to infinity. I put the b in, so I got a b, I got a minus b e to the minus sb over s minus, which makes it a plus 3 e to the minus s 3s divided by s, okay, minus that interval, which is going to be minus a minus, that becomes a plus, it's going to become another minus, we'll put it there though, minus e to the minus st over s squared evaluated 0 and b. Okay, when I put the b guy in, I go to infinity, I get 0. When I put the 0 guy in, I get a 1, and the minus guy becomes a plus. So this guy becomes, but b, I'm not going b, I'm going 3. B goes to infinity, that's right. But I'm 0, 0. This is a 3 down there. Not a 0, this is a 3. All right, so when I put the b in, it goes away. But when I put the 3 in, I get a minus, I get a plus. Okay, so this is going to be 3e to the minus s over s minus, that guy goes to 0. This is a plus sign, e to the minus 3s over 3, and there's a 3 there, and this is an s squared, not a 3. Wow. Did I talk my way out of that, or what? Oh, well, it looks like that's right. So now we're going to come back up here, grab this guy. Well, thank you very much, computer, for being so cooperative in your grab. Okay, so I'm going to grab that guy. And I'm going to put him right here. Okay, and then we're going to erase that part. And then we're going to say plus 3e to the minus 3s over s. Well, look at this. I got 2s minus 3s, right? And I have 3 of them and I have 2 of them. So that means I can get away with plus 1 of them. Oh, luck. So I got plus 1 of them, plus e to the minus 3s over s squared. Ta-da! Oh, pain in the butt. Okay, I agree. Total pain. So now we have most of the guys, except the unit step function guy. What I left out is I didn't bring my gamma function table. You know, have you seen a gamma function table? Okay, we'll do it. What's 3 factorial?
6.
6?
Mm.
What's 3 double factorial?
3.
3, right. All right, so what's 4 double factorial? 8. All right, so what is 2.5 factorial? Anybody have a graphing calculator with them? TI 8689? Take your TI 689 and put in 2.5 factorial. What do you get?
Denominator.
Boy, what a stupid calculator. What is it?
That's what I got.
Oh, you don't have a TI 89. You need a graphing calculator. What do you got there, Andy?
I got 83.
Oh, forget it. Bunch of, I mean, you guys are supposed to be the top brightest students at Iowa Western, and you don't even have a graphing calculator worth beans? I mean, really? I mean, what's mom and dad thinking about here? Anyway, in order to find 2.5 factorial, you need a gamma function table, and let's see if our book has one. Maybe they do. I normally bring one, but it's stuck in the other. So gamma function, page 250 and 268. 268. Yeah, 250. Did I say 250? Gamma, yeah, there's the gamma function. So the gamma function of x plus 1 is going to be x, the gamma function of x. So 2.5 factorial, we'd use the gamma function, and we'd end up getting x is 1.5. So if x is 1.5, then this would be 1.5 gamma function of 1.5. So 2.5 factorial would be that, and then this would be 1.5 times 0.5 times gamma function of 0.5. All right, now, what's the gamma function of pi? Anybody know the gamma function of pi? I'm sort of thinking it's E, but I'm not sure. I don't remember. Somewhere in the book it's probably going to tell us what the gamma function of pi is. It's some funny thing that you'd never think of.
You know, half is the square root of pi.
It's the square root of pi?
No, half is the square root of pi. So.
Oh, half is the square root of pi? Oh, the gamma function. Oh, okay, so the gamma function of 1/2 is the square root of pi. So isn't that fun? All right. Well, next time we're going to need the gamma function because of the Laplace transform that's, where the heck is it? Where did it go? It's, yeah, sitting there on page 271. If I take t to the a, where a is greater than -1, I have to use the gamma function to find it. But if I don't have a gamma function table, I'm sort of hosed city. I can't find it. So if I have t to the 3.5, so I could find t cubed. I know what that is. That's going to be 3 factorial divided by s to the 4th. Okay, because that's the guy before it. But if I have t to the 3.5, then I have to take the gamma function of 3.5 plus 1 divided by s to the 4.5. All right. Now, luckily, I think this is the only section where we actually use that. And I don't recall it being on the test. But I apologize for not bringing my gamma function guys with me. Okay, so now we're going to work some problems. And gamma function is something that's used in differential equations and nowhere else. I think it might be used in statistics someplace, but I'm teaching a statistics class and I don't remember ever using it. So, all right, so we're going to know 1 through 33 double odd. All right, so I already did 2, I already did 4, I already did 6. Let's do 10. Okay, so number 10, f of t is equal to minus 1 for between 0 and 1, and it's 0 between 1 and infinity. Okay, so that's our function given to us in a graphic form, right? All right, so f of s integral 0 to 1 of minus e to the minus st dt plus integral 1 to infinity of 0 times e to the minus. Now everything should be that simple, right? I mean, that's this becomes 0 and half my problem goes away. That's okay, right? Minus e to the minus st divided by minus s evaluated at 0 and 1. Okay, so those guys go away. I put a 1 in. E to the minus s over s minus 1 over s. Is that okay? All right, number 10. Looking at number 14. Number 14. Oh, I hope not. I mean, that was so pathetically easy that I doubt if you really wanted me to go back. I mean, I can raise it up on the screen some. I can make this 0 look more like a 0, right? But other than that, not much I can do with that. Huh? Good enough? All right, going on to number 14. Okay, so I'm looking at number 14. F of t equals t to the 3/2 minus e to the minus 10t. And find the Laplace transforms of these problems. Well, want the Laplace transform of that. So I need the Laplace transform of t to the 3/2 minus 1 over s plus 10. Okay, because I took that right off my table. I didn't have to do anything with that. So now I'm looking at the Laplace transform of t over 3, and now I'm stuck with my I'm going to have to find the gamma function of 5 over 2 divided by s to the 5/2. Okay, so I gotta find the gamma function pi over 2. Okay. Yeah, without a gamma function table. What a bummer. Okay, I got it. So, the gamma function of pi over 2 is equal to pi over 5 over 2 times the gamma function of 3 over 2, which is equal to 5 over 2 times 3 over 2 times the gamma function of 1 over 2, which is 5 over 2 times 3 over 2 times the square root of pi. There we go. Oh, yeah. 15 over 4 square root of pi. See, I did it without a gamma function table. All right, so final answer. Final answer, f of s equals 15 over 4 square root of pi divided by s, that's an s. S to the 5 halves, is it plus or minus? Minus 1 over s plus 10. Oh, what could be more clearer than that? I mean, that was so clear. I don't know why we didn't cover that in chapter 4. How to do the... Well, anyway, I probably have some idea why we didn't do it.
How'd you get the S of pi over 2?
Because in your Laplace Transform table, it says that the Laplace Transform of t, on page 271, of t to the 3 halves is going to be the gamma function of 5 halves divided by s to the 5 halves. See that? T is 3, A is 3 halves, right? What's 3 halves plus 1? Oh, that's where I got it, right. So
Oh, you're looking at T to the A?
yeah, T to the A, right. So I have T to the 3 halves. That means my A is 3 halves. A plus 1 is 5 halves. That's what I'm finding the gamma function of, and that's what the S is why it's S to the 5 halves.
And then for the gamma functions, are we just going to look up the table for those, I'm guessing?
Well, if I would have brought the table with me, that's what I would have done, yes. But without the table, then I'm stuck with doing something different. So, you know, if I want the gamma of 92 eighths. Okay, I want that. That's dumb. I don't want that, do I? Of the gamma function of 13 halves. That'd be better. All right, so what would that be? Well, it'd be 13 halves times 11 halves times 9 halves times 7 halves times 5 halves times 3 halves times the square root of pi. Ta-da! So that's how I would solve that problem. But if I had something other than halves, I couldn't use the square root of pi anymore, and I'd have to go to my gamma table to get the thing. And like maybe next class period I'll remember to bring it. Maybe I won't. Okay. We'll do 16 next because it's easy. Number 16. F of t is equal to sine 2t cosine 2t. F of s equals. Okay, so I'm going to have square root of 2 s squared plus 2 plus s over s squared plus 2. Done. Done? Is it really that simple? Yeah. The cosine of kt, well, this is a 4. That's a 4, that's a 4. This is a 2, dummy me. All right, that's better. Yeah, the cosine of kt is s over s squared plus k squared, and the sine of kt is k divided by s squared plus k squared. I'm done. Should we do 22 or not? I don't know. 22 looks, well, we got 2 minutes, right? Won't be a problem. F of t hyperbolic sine squared 3t. All right, well, let's see. Hyperbolic sine of 3t would be e to the 3t minus e to the minus 3t divided by 2, right? And if we were to square that, we would get something over 4, right? And we get e to the 6t, and then we get minus 2 plus e to the minus 6t. Would we not? Is that what we would get? Square that guy, square this guy, 2 times those guys multiplied together? Yeah, okay. So I've got e to the 6t over 4 minus 1/2 plus e to the minus 6t over 4. And I'm going to take the Laplace transform of the whole thing. So this is going to be 1/4 1 over s minus 6. This is going to be minus 1/2 1 over s. This is going to be plus 1/4 1 over s plus 6. That doesn't look like a quarter to me. All right, well, that looks good. We'll take out a 1/4 and call it 1/4 1 over s minus 6 minus 2 over s plus 1 over s plus 6. All right, looks good enough. Now, we could find a common denominator, right? And we probably should. We should probably find a common denominator and put it under the whole thing. Do we really want to do that? Yeah, we probably do. Okay, so 1/4. My common denominator is s squared plus 36, s squared minus 36, s squared minus 36 times s. And on top, I've got s squared plus 6s. I got s squared minus 6s. And then here I've got minus 2 s squared minus 36. All right, well, let's see. So I got plus here, minus there. They go away. I got 2 of these, and that one goes away. And all I have is a minus on top. So it looks like I'd end up with, and 4 goes into 36 how many times? So I'd have 9 over s squared minus 36. Okay, good enough? Like I say, I would have stopped there so that was good enough, but you could go on if you wanted to. Now we get to go the other way. And we'll start with 24. I don't want to start with 24. Number 24. Okay, so f of s is s to the minus 3 over 2. Is that what that says? All right, so in order for it to be minus, oh, okay, not a problem. So this is 1 over S 3 over 2, right? All right. So that means this is the t of 1/2, right? T of 1/2 because I have S1 plus 1/2 down there, and then I should have had the gamma function up here of a 1/2, so I should have a square root of pi up there, and I don't. So I'm going to have 1 over the square root of pi because it went away. Oh, there we go. Number 24 done. Nothing, all my long sleeves? Yeah, must be something up my sleeve. 26 is too easy. That's just e to the minus 5t. 28. F of s is 3s plus 1 over s squared plus 4. Well, can we factor the bottom? No. If we could factor the bottom, then we could do partial fractions. We can't factor the problem. But we can say 3s over s squared plus 4 plus 1 over s squared plus 4, right? And we could say f of t is equal to 3 cosine 2t, right? Plus, and I gotta, if this is k squared, I need a k on top. So I need a 2 on top. So that means I need a 1/2 out there. 1/2 sine 2t. So I just did the inverse Laplace transform with that guy. And after you do a couple 100,000 of these, it'll be just that simple, right? And by the end of the week, we will have done that many, probably. We'll do 30. Number 30. F of s. 9 minus s, 9 plus s. 9 plus s, 4 minus s squared. 4 minus s squared. F of s. We don't know much, right? So the only way you get an inverse Laplace transform is from the table of Laplace transforms, which we have very few of, right? But if I say this is minus 9 minus s over s squared minus 4, and then I go looking at my table again, I see that that is the hyperbolic sine, hyperbolic cosine guys, right? So this could be minus 9 over s squared minus 4 minus s over s squared minus 4. And the minus s squared over 4, that's the, comes out to be the hyperbolic, if I could spell hyperbolic cosine. Hyperbolic cosine of 2t. So that I got that guy. Now I got to get this guy here. And I need a 2 up there. I have a 9. So if I bring the 9 out, and I divide the 9 by 2, and then I go and I put a 2 up there, then I end up with this guy being, and what did I do? I brought the 9 out, so the minus sign came with it. Okay, so now I've got minus 9/2 hyperbolic sine 2t. Oh, and the problem set goes to 33, so I guess I've gone far enough. Don't do the problem set after 33. Don't even think about it. One of you were thinking about it, I can tell. Okay, good enough? Or do you want me to do 32? Yeah, you don't. You do?
Sure.
Oh, I don't know. Number 32. All right, so again, we can only do problems that we have in our table to do. E to the minus 3 s, right? So we go back to our table and we say, well, what are we going to do about that? Okay, so I'm going to write this e to the minus 3s divided by 2s. Okay, and I'm going to make that 1/2 e to the minus 3s over s. Okay, so this is the it's going to be 1/2 the unit step function of t minus 3. I'm done. You know what the unit step function is? You don't? How did you guys make it to this class without knowing what the unit step function is? Oh, gee. All right, so here's the unit step function. It's 0 at 0. Boom, it goes to 1. Boom, it goes back to 0, 3, 1. That's the unit step function. Okay, so t minus 3. When t is 3, this becomes 0 again. When t, at t is 3, it becomes 0. So it goes up, goes down, boom. I'm sure that's covered someplace in the text. Okay, time to go home early. Are we convinced? We haven't solved the differential equation yet. What's the name of the class? Differential equations. We're supposed to be solving them. We made it all through section 4.1, and we didn't even solve a differential equation. What good is this? Now the good news is this book has a Laplace Transform table in the front cover, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a huge number of Laplace transforms already solved for you. All you have to do is just go get them. And then the other thing is, what? I guess that's enough, right? I have another Laplace transform table that comes from the Tech Math book. That when I find my gamma table, I'll also find my Laplace transform tables. I'll give those to you too. They have some other ones. If you get a handbook of chemistry and physics, it'll have 250 Laplace transforms in them already made for you. Okay, so that'd be cool too. Not you don't need them for this class, but some other class.
Can you go a little bit on the slide, please?
You want me to move up?
Yeah. That's fine.
Yeah. So looking at that, just looking at it without context to being in chapter 4 or anything else, I look at that as
Is that
it's all Greek.
that's just 2s to the negative 1?
2 times s to the minus 1. Oh, did I put the 2 in the wrong spot? Bummer. 2, 2, 2. There, is that better? Yeah. Much better now. Wait, how did that 2 get down below anyway? How did I do that without anybody catching me until way late in the issue, That's pretty clever the way I did that, wasn't it? I was just trying to see if anyone was paying attention out there.
They took the front row.
Yeah, that's right. Those guys in the front row letting you guys down again. All right, Control, Shift,